Alright people, let's start on chapter 9, alcohols, ethers, and epoxides. We're going to just start with the basic stuff. Good news, a lot of this chapter is going to remind you quite a bit of elimination and substitution reactions, because we're going to look at these compounds and then look at the reactions that they're going to do. And with us today is a little robot. I call him Le Chatelier. So, alcohols, ethers, and epoxides. Let's just go over some general stuff. Recall, alcohols have the hydroxy group. We have primary, secondary, tertiary alcohols based off of the number of R groups bonded to the carbon that is bonded to the oxygen. A few other things, if the carbon containing the oxygen is also double bonded to another carbon, we call that an enol, more on that later. And if the carbon containing the oxygen is part of a benzene ring, a phenyl ring, we call that molecule phenol. Now, some people will call it phenol, just so people don't get so confused between phenol and phenyl. I prefer phenol. Ethers. We have symmetrical ethers, where you have ROR, and those two R groups are the same, such as two methyls. Unsymmetrical ethers, two different groups, CH3, CH2, CH3, unsymmetrical ether. A new one you might not have heard of is an epoxide. That's where you have a carbon single bonded to another carbon, but both those carbons are bonded to an oxygen, so you have this oxygen, carbon, carbon, three-membered ring. That's an epoxide, also known as an oxirane. And since we all know about triangles, we know that's a 60-degree angle instead of a 109.5, so that's a fairly strained system. All right, let's look at some nomenclature. Good news is we've already gone through the nomenclature of alcohol, so we already know the deal here with the carbon containing the OH getting the lowest carbon number, 1, 2, 3, 4, 5, 6. Note the first branch is at carbon 5, closest to this end. However, with alcohols, we have to give this carbon here containing the oxygen the lowest number, so this is 5-methyl, 3-hexanol, or as IUPAC will now say it, 5-methyl-hexan-3-ol. All right, and we've already gone through the other naming of these molecules, of these alcohols, so let's move on to naming ethers. All right. When naming ethers, small ethers at least, you gotta love the common method of naming it. You just name what's on either side. For right here, here's our oxygen. We have an ethyl on this side, an ethyl on the other side, diethyl ether. For this molecule here, we've got a tert-butyl group on this side, a methyl on this side. Recall from our naming that when naming a tert-butyl, alphabetically we start with B. And so this would be tert-butyl methyl ether. If your molecule is large, then you're probably going to want to name it according to the IUPAC method. And the IUPAC method it's a alkyl oxy kind of way. So this is a methyl group on the oxygen. This is a methoxy. This is an ethoxy. This would be a tert-butoxy. So with IUPAC, you find the longest chain on whichever side of the ether has the longest chain is your parent molecule, and then the other side is your oxy group. So here we note, okay, our longest chain, 1, 2, 3, 4, 5, 6, 7, 8 carbons. That's an octane as our parent. Our branch is this ethoxy, so this would be 4-ethoxyoctane according to IUPAC. Ooh, what would IUPAC call this? Our longest chain is 2-ethane. They would call this ethoxyethane. Yeah, I like diethyl ether better. All right. Epoxides, naming epoxides. Some people get real jazzed about naming epoxides. I do not, so I'm not going to require you on the exam to name an epoxide. However, you should be able to pick out a molecule, know that it's epoxide, and figure out which name it is, what the name is. So note, you have to tell what two carbons the oxygen is on. This would be 1,2-epoxy cyclohexane. Makes sense. Right here, what do we have here? Well, IUPAC would say our longest chain, and both carbons of the longest chain must contain the epoxide, or the oxygen of the epoxide. So we have 1, 2, 3 carbons in our longest chain, so that's a propane. The oxygens between carbon 1 and 2, and we also have a methyl on carbon 2, so this would be 1,2-epoxy 2-methylpropane. All right. As I said on the exam, I'm not going to require you to name it, but if I said, okay, which of these molecules is 1,2-epoxy 2-methylpropane, I would expect you to be able to pick that one out. Note, as these are sometimes called oxiranes or technically alkene oxides, one could call this group right here the oxirane, and then you've got a methyl on carbon 2, a methyl on carbon 2, 2,2-dimethyl oxirane. I don't care for that, but yeah, I'm going to have to go with IUPAC on this one. All right, physical properties, you can read about those. There's an interesting class of molecules. Honestly, at this point in the semester, being you're at home or something, read up about these crown ethers. They're pretty cool, but we are not going to discuss these crown ethers or some of these crazier molecules. We just don't have time this semester. Sorry about that. We lost that whole week and whatnot. All right. Next page. All right, how do we make these molecules? How do we prepare alcohols? How do we make them and these ethers and whatnot? Good news, we've seen this before. Yeah. How do you make alcohols and ethers? Simple, an SN2 reaction with an alkyl halide. Start with ethyl bromide here, and we know, nice SN2 reaction, bromine, good leaving group. Hydroxide, good nucleophile. Hydroxide will attack that carbon, kick off the bromine, SN2 because it's primary, and make ethanol. You can do the same with ethers. Just take an alkyl halide and react it instead of hydroxide, react it with methoxide or ethoxide or something like that. Again, primary alkyl halide, strong nucleophile. SN2 reaction to give this molecule here, this methylpropyl ether. And here, let's make diethyl ether. Take ethoxide with ethyl bromide. We make our symmetrical diethyl ether. These two reactions we just did are our first example of what we call named reactions. These reactions are known as two reactions of the Williamson ether synthesis. When we are discussing organic chemistry, organic chemists, and you will, because you will become organic chemists or some derivation of that, you need to know the people that came up with the reaction such that when you hear the name of the reaction, immediately in your head you say, oh, okay, I know what that is. Because what happened was Williamson was wanting to make ethers, and so he made this ether, said, oh, that's cool. Is this the best way to make an ether? And so Williamson spent years and years and years finding the best way to make a whole bunch of different ethers, published his papers. Later on, someone said, oh, I need to make an ether. How do I do it? I don't want to spend 10 years finding the best way if someone else has done it. Has anyone else done it? Yes, looked up the literature. Williamson has done it. And so someone else says, okay, which way to make ethers? And this guy said, I do the way Williamson did. And the next person, okay, now I need to make ethers. Oh, use Williamson's method. Method for what? Oh, Williamson's ether synthesis. Okay. And so your name gets attached to the reaction. If you do a reaction that's very important and people find very useful, your name gets attached to it. Note, you don't get to attach your name to it. The chemistry community attaches it just because it's so useful. And so as we go on, especially when you take organic 2, we develop more and more of these named reactions where, oh, as soon as you say the name Williamson, right in your head should be, okay, SN2 reaction of making ethers. We'll find more of these reactions, not so many this semester, but next semester we're going to be talking about it, such that when you're at a conference or whatever and you are talking with someone about your methods of making this molecule, and someone said, oh, well, how did you make this and such like that? They said, well, I started with a Williamson ether synthesis, followed by a Friedel-Crafts, and then a Diels-Alder, and finally ended up with a Suzuki. And the person listening to that says, oh, yeah, I see. Just by the names, you should be able to know what the reactions are. All right. Well, Williamson spent a lot of time on this, and then he looked at this. All right, I want to make this ether, this isopropyl methyl ether here. One could think of two ways to do this. You could start with a methyl bromide and add this isopropoxy group to it and do SN2 this way. Or one could start with the secondary isopropyl bromide and add methoxy to it. And what Williamson found was both ways will work. However, since this is going via SN2, we know that primary substrates are more favorable for SN2. Therefore, the less sterically hindered alkyl halide substrate is the best way. So here, this is a secondary substrate, strong base. You might run into a little bit of E2 happening here. Here is a primary substrate, strong base, more likely to get this reaction to work, even though we got a bit of steric hindrance on our nucleophile. Williamson found out through many, many experiments that primary substrates, less sterically hindered substrates, less sterically hindered alkyl halides are going to do the reaction much better. Okay. The next question is, all right, where do we get our reagents? Good news, these alkyl halides usually can just be purchased. You can buy them. We're going to find out in a day or two how we make them. But our epoxides, methoxides, isopropoxides, they're pretty reactive beasts, and they don't transport all that well. So, let's see, sodium methoxide, that can be purchased. That's pretty good. But some of these others are, you know, especially a larger group here, you just can't buy that. You have to make it yourself. And good news, we have a very nice way of making it. So say you wanted to make ethoxide and you didn't want to buy it, the best way to do it is take just ethanol. And boy, you can buy ethanol no problem. And react it with sodium hydride. Note, this is a chapter 2 acid-base reaction where hydride is going to attack this hydrogen, and this lone pair will go on that oxygen to make sodium ethoxide and H2 gas. This works out really well because if you look at pKa's, the pKa of the acid is, what's this, about 16 for ethanol. The conjugate acid is H2, pKa of 35. So this equilibrium lies well to the right. And as a bonus, you make H2 gas, which goes away. It's a gas. It leaves the reaction, so you don't even have to clean this up. You've just got your sodium ethoxide, your other product left. No separations required, or at least not too bad of separations. Okay. So, if you take, say, cyclohexanol, add NaH, and then add CH3CH2Br, what will happen? Well, sodium hydride takes off this hydrogen to make the cyclohexoxide, or cyclohexane oxide here. And then that will attack this carbon here in an SN2 fashion, kick off the bromine. You end up with CH3CH2O cyclohexane. All right. We will show various ways to make an epoxide. The first way to make an epoxide is just with an intramolecular SN2. What if we have one carbon that contains the OH? that we can deprotonate to make the oxide, and the other carbon bonded to it contains a leaving group, such as bromine. Well, if you react a base like sodium hydride, it will take off this hydrogen, giving that oxygen a negative charge. And then that negatively charged oxygen can attack this carbon, kick off the leaving group, and you've made your epoxide. I think there are better ways, especially if you're starting with a double bond, there are better ways to make epoxides that we will go through. But if you don't have a double bond and you happen to find yourself with an alcohol that has a halogen on the next carbon over, then, you know, this will work. All right. So, now that we've made our alcohols, what can we do with them? I have an idea. Let's end this video as an intro and get on to reactions in the next video.